Okay. So we've talked about mass spectrometry and how mass spectrometry can describe the mass of an atom or the masses of atoms that go into the mass spectrometer. And we can use that to find which isotopes are present and the average atomic mass. Something similar is photoelectron spectroscopy. Sometimes referred to as PES. And in a similar way that we do mass spectrometry, we put a sample into a machine. We put a sample into a different type of machine, a photoelectron spectroscope. And what it does is it uses Coulombs Law to figure out the energy of the individual electrons. How much energy each electron in that atom has. And the way it does this is it hits each electron with high energy electromagnetic waves, like X-rays. So X-rays hit the atom, and if they have enough energy to remove the electron that they hit, it will come off. It will be removed. And we know, based on Coulombs Law, that electrons that are closer to the nucleus require more energy to remove. Because the Coulomb's force, the force of attraction, is greater when this distance is smaller. The smaller the distance, the greater the force, therefore more energy to remove it. Okay? There are some other things to take into account here, so let's look at the orbital diagram for this. If the nucleus is down here, okay, so if I'm adding energy to this atom, these outer electrons take the least amount of energy to remove. They're the easiest to remove. So these fly off first. They get pulled off first. And the photoelectron spectroscope is able to record how much energy they have as they're removed. The amount of energy they have when they're removed is related directly to the amount of energy they had to remove it, and it records that. Each electron that gets removed possesses a certain amount of energy, and that energy is directly related to its location in the atom. Electrons out here have lower energy. Electrons in here have higher energy. It takes more energy to remove them. Okay, so as we're removing electrons, this one takes the least amount of energy to remove. Then this one takes a very, very similar amount of energy, just slightly higher. That's because in the beginning, we have electron repulsion between these two electrons. They're kind of pushing away from each other. So this one is slightly easier to take than the second one. Then we have these. These are more difficult than these. The first one is the easiest, again, because of electron repulsion. And then the second, and then the third, and then the fourth, and then the fifth, and then the sixth. And then you're down here. In this orbital or sublevel, the first one is easier. The second one is a little more difficult, but they have very similar energies. Then in the 1s, this one is a little easier. And this is the most difficult electron to remove. It takes the most energy because it requires the most force. Okay, so if we look at a PES for this, we have number of electrons on the y-axis and the amount of energy in kilojoules per mole on the x-axis. Here's the weirdest part about PES. Many times, not all the time, but many times, they'll have the highest energy here and the lowest energy out here. It's backwards. And that's because they're trying to represent this, the origin, as the nucleus. Okay, so as we look at these electrons, we start taking electrons off. We remove this electron and this electron. Those have very similar energies, right? Same thing here. These two electrons have very similar energies. They show up out here, low energy, as a peak, like this. They're a peak because they don't have the exact same energy. One is slightly lower than the other because of electron repulsion, but they're kind of in the same spot. The height tells you the relative number of electrons. Okay, then we come down here. These 6 all have a similar energy, very close together. Some slightly higher than others. Okay. Then we're down here, these two also have similar energy, very close energy to the P. And then these two require the most amount of energy. And they're down here. So we have highest energy, hardest to take, strongest force, least force, least amount of force, least amount of energy to remove. These are your valence electrons out here, farthest from the nucleus. These are your inner shell electrons. Now we can use this PES and label it. This is 1s, and there are 2 electrons. Then we go 2s, there are 2 electrons. Then 2p, and there are 6 of them. And then 3s, and there are 2 electrons. You see that the height is relative, 2, 4, 6. If you're ever asked to draw one on a test, do your best to show that relative height. And then we have 1s2, 2s2, 2p6, 3s2. So this has to be the PEs diagram for magnesium. We use PEs diagrams to identify atoms, to look at their electron structure. And it all works because of Coulombs Law and the amount of energy it takes to remove every single electron. And there's this misconception that we could never remove these electrons in here. You can. It just takes a huge amount of energy to remove them because they're pulled so tightly by the nucleus. Let's do one more example. So let's say you're given a PES that looks like this. And your only job, you'll be given this, and you'll be asked what element is being represented here. You might want to label it. And then you would know that it's 3s1, so it has to be sodium.